n minus 1 squares. Together with, well, what's the only other possibility? The only other possibility is there's not a domino there. Well, if there's not a domino there, then the tiling essentially splits into two tilings, right? Because that means that you can divide at this line and you got the two halves. So it's going to look like this. Right, where there's a dividing line here, and now you have to tile this side, which is going to be m minus 1 things, and tile this side, which is going to be n things. And now we're done, right? Because think about it, what counts, remember, we have to shift indices. How many ways are there to tile this? Well, that guy. How many ways are there to tile this? Shifting everything, that guy. Domino is weighted by a t, m minus 2, shifted, n minus 1, shifted, poof. Okay? Now, why did I choose this out of the many, many identities there are for Fibonacci numbers to prove? Well, it's because of the following.
But there's no s here?
No s, just t. Right, there's no, right, just because there's a dividing line here doesn't mean that either of these have got, right, this could have gone over. It just means that it falls apart. It doesn't give you any restriction on what goes on either side. The reason I want this is because of the following corollary. I should probably say theorem because it's our main tool here. Okay. How does one prove something if one has no idea how to prove it other than anything else? Induction, right? Induction is kind of the default proof. So in order to induct, we need a recurrence. So since we're trying to prove something about these guys, we better have a recurrence relation for them. Here's the recurrence relation. It is n plus 1, n plus n, choose n minus 1, plus m minus 1, m plus 1, choose m. Notice this looks very much like the binomial recurrence, as it should, because that's one of the special cases. Right? If we drop these guys out of the picture and just look at the tops and the bottoms, it is the binomial coefficient recurrence. Okay, and the proof of that's really simple. Let me put it, where shall I put it? I'll put it here.
It's not m plus m minus 1 at the top?
I'm sorry, what?
It's not m plus m minus 1?
Oh, yeah, of course, yes. It is the binomial recurrence if I write it correctly. Thank you, Doron. Going too fast for my own good, as usual. Just a little slower. Okay, so what does the proof look like? Well, again, it's really simple. Just as with ordinary factorials, you can use the same sort of tricks about, right? A factorial is you pull out the first term and then you have a factorial of what's left. So we could write this as m plus n times m plus n minus 1 factorial over m factorial. Why do I want to do that? Yeah, because I know what n plus n looks like. That's what I just proved. Okay, so let's plug in from the corollary what this guy looks like. And what I'm going to do is I'm going to leave this upstairs in the fraction. I'm going to take this outside. I'm going to leave this upstairs in the fraction, and we take these guys outside. So that will give me n plus 1 is outside from there, and then I leave the m upstairs. And then I do the same thing with t times n m minus 1 on the other. Right. Why did I choose to do it that way? Yes. I'm seeing the correct hand motions.
Yes.
You can cancel, right? This m is going to cancel into that m factorial, leaving me with n minus 1 factorial. Similarly, this n is going to cancel into that n factorial and leave me with n minus 1 factorial. And now look what I've written down. n plus 1, that's this n plus 1. M plus n minus 1 factorial over m minus 1 factorial n factorial. I think that's this. Tm minus 1. Yeah, can you keep up with that with the camera? Oh, you're just focusing on that. That's probably a good idea. Oops, there's a T there. See, the good thing about doing all the proofs is you catch your mistakes. Right? There's got to be a Tm minus 1 because that's what we took outside. And then the rest of it is that. Well, now that we hopefully have the correct recursion on the board, we can go forward. Are there any, so this is a good stopping or breaking point for any questions?
But the most straightforward way would be divide both sides by something, and then, I mean, it's the same thing, but you just divide by m plus n minus 1.
I mean, you can do all sorts of things if
Yeah.
you wish.
No, of
is
course,
the-
not hard, but
Yeah.
a more verification is more.
Ah. But this is in fact exactly the form we wanted
Yeah.
in order to get our main theorem. So that's the reason I've chosen to write it down this way. There are many other recurrence relations you can get like this. This is like, again, for those of you that know Q theory, you know that the Q analog of a statement is usually not unique because there are these powers of Q that appear, which when you let Q attend to 1 disappear in the original statement, and different powers of Q often work. So there's many ways to skin things in the Q world, and there are also many things to skin things in the S and T world as well. Any questions or comments before we go? Okay, so we're very close. There's just one more set of definitions you need to see. So we're going to need to talk about integer partitions. So a partition, lambda equal lambda 1, lambda 2, down to say lambda r, is a weakly decreasing sequence of positive integers lambda I called parts of the partition. Okay, so just take some weakly decreasing sequence. And the way we're going to think about these is in very geometric terms, in terms of something called the Ferris diagram. So the Ferris diagram lambda. So it has R rows, and R here is the number of parts you have of left justified boxes. And the lambda i's tell you how many boxes to put in row I. So lambda I boxes in row I. Again, an example. We'll make this totally clear. Say we took the partition 3, 2, 2. What would its Ferris diagram look like? Well, that means we're going to have 3 boxes in the first row. The next row will have 2 boxes, and we'll put it left justified under the next row. And then the final row will also have 2 boxes left justified under. Okay. Hopefully pretty straightforward. So,
That's the Young diagram. The Ferrari diagram is this dots. These boxes is
yeah.